you want me to introduce it?
No, that's fine. I'm just, hopefully that's just showing the right screen in the Hangout.
Yeah.
Okay, well, we arrive. So, welcome back. Thanks for coming back. We didn't scare you away. Yep. Didn't scare you away yesterday, so that's good. Agenda for today is to talk about text and sequence data in general. Then talk about autoencoders and what you can do if you don't have labels for your data sets. Autoencoders are sort of more stuff that you can do with unsupervised learning. Then we'll also talk about a little bit more on how to actually tune networks and go through some more in-depth examples of sort of slightly bigger, more realistic applications. If we have time, we'll talk about reinforcement learning some more, and then we'll wrap up with sort of summary and what's happening more on the research side and things people are excited about today. As usual, ask questions, please. So words. We'll talk about translation, sentiment detection, other things you can do with text, though not all of them. How do we actually make networks that more or less understand language in some way? One of the challenges is the fact that there are so many words in language, so it's important to represent them in some reasonable way. And we'll talk about how to do that. And then we'll talk about recurrent networks, which help us help the network kind of remember what it's seen before as it's processing later data in some sequence. Okay, so we'll do that. Let's start just by talking about language, right? And why this is actually interesting. So obviously, on the potential side, if we can get computers that actually understand language in some deep way, that really opens up lots and lots and lots of potential applications. And we see some of them already today, right? Siri, Alexa, etc. Can understand certain simple queries. And at the same time, we still see how much is left to go to be able to really, tell your computer, here's what I'm struggling with today. Please write a poem about this. We're pretty far away from that. Read text, write text, etc. Traditionally, and to some degree still today, but when people started trying to do AI back in the 60s and 70s and 80s, especially 60s and 70s, there was this notion that language, you could just, if we're clever enough, we could just describe it, right? Here's what English is. Here's all the rules and all the exceptions and all the exceptions to the exceptions. And so we can, sentence diagram our way through all possible correct sentences. And if they're not correct, why would you possibly want to use them? And then once we did that and we understand the meaning of all the words, we can just have this giant database that describes English. And that'll be that. We can just use it for various applications. This is a classic example in linguistics of a perfectly valid grammatical sentence that means absolutely nothing. This turns out to not work very well because language is weird. And really starting in the 80s, and I think actually starting at IBM, if I remember correctly, they started this much more statistical approach that said, you know what? We're never going to be able to write down all the rules. Let's just try to infer some of the patterns and how people actually use language. We'll read a bunch of text, we'll count things, and then we'll use that as a model to try to understand what kind of things are actually valid sentences, for example. It's less precise, but it's much more flexible. So here's one example, just to give a flavor, right? If you're looking at this frequency curves of the use of Apple, for some reason, people started putting the word Apple at the start of sentences much more frequently around 1970 something. But that must have been it, right? For some reason, capitalized version just became much more famous. As a computer, it probably doesn't know why, but it knows that, hey, something happened, and so now in the middle of a sentence, if I see a capitalized Apple, I'm not surprised after 1970 something, and I am surprised before. And so if you're analyzing text from different times, you might actually analyze it differently based on what you know about word frequencies. Obviously, this is a really simple example, but we'll see what you can do with networks, et cetera, that uses the same basic principle. Yeah, so what's hard about text? Maybe I will not make this a rhetorical question. I don't know if you have any experience with text processing or just intuition for it. Maybe I should have said language.
There's a lot of references to other things. So you could name someone person, and then you start referring to that person as the provenance. It's not always that you're always describing everything. So how do you start referring?
Right. Lots of things we say refer to other concepts or ideas or things that we mentioned 3 chapters ago, and possibly refer to it in some oblique way. That darn guy refers to the person that was being obnoxious 3 paragraphs ago. How do I know that? That's one good example. There are many others. Ambiguity, right? So here are some examples. The tank is full of, what does tank mean? I don't know. Is the next word going to be soldiers or nitrogen? Right? The word ground, is it a noun, a verb? Does it mean dirt or the floor of this room or to ground some electrical circuit? Jaguar is a great example. I think I have it on the next slide. Here's some meanings of Jaguar. Cars, aircraft engines, shield supervillain, band, a pseudonym of some other person, Kenyan musician, 3 different films from different years, an Atari Jaguar, a supercomputer, a CPU design. Oh yeah, but wait, there's more. A bunch of different sports teams, military weapons. But wait, there's more. Right, so when you read Jaguar in some text, maybe if you had that database of what English means, you might have like 2 or 3 or 4 of these meanings, but it's hard to have all of them. And even if you have them, how do you know which one is being referenced in the context you're in? And even worse, sometimes maybe it's 3 or 4 of them at the same time. Right? The Jaguar, the whatever sports team is named after the Jaguar Warriors of the whatever, and they like to drive Jaguar cars. I go, oops, 1 sentence, 3 different meanings for the same word. Yeah, so the other thing is it's not anywhere close to unique, right? If you're trying to express ideas, there are many, many, many different ways to say the same thing. And so if you're trying to write a program to say, okay, sentiment analysis is a classic example where you start. It's sort of a relatively simple problem. It says, what are all the good ways I can say something positive about IBM? It's kind of hard to enumerate them. And so somehow you have to figure out how to figure out the meaning of sentences you've never seen before. Context, sort of the same thing in terms of what you're referring to. Often there's assumed context, right? So when you read "I pressed the suit," even if I know you're a lawyer, did you press it before or after going to work? Right, would mean different things. Then there's even more complicated things like humor. I found a great set of papers and blog posts and people trying to make computers that are funny, that tell jokes. It's not very far along, right? So both understanding why is something funny or is something funny, and even worse, trying to generate humor is really hard because it's kind of hard to explain sometimes why things are funny. And then Twitter is its own crazy language that has some resemblance to English or whatever language you're interested in, but only vaguely. So let's start with thinking about, like I said, sentiment detection, and thinking about how we might actually try to tackle this problem. So there's this classic data set from IMDb of movie reviews, 25,000 movie reviews labeled as positive or negative. And the goal is to say, okay, given a bunch of labeled data, so still in the supervised learning space for now, how do I predict positive or negative? hopefully with high accuracy. And yeah, so let's just jump into some code and look at it. So first I have a book, a notebook that shows basically a data set, right? So kind of just loading it, and let's look at what this kind of data looks like. And then we'll actually talk about how we might tackle it. If I can find my mouse. So we'll come back to approaches to tackling this kind of thing in a bit. But here's the data set. So you can grab it from the Stanford site. Right, so setting up random stuff. One note for anyone trying to follow along with the code. There's a bug in the Keras built-in IMDb little library. And so you have to actually go and download like an old version of the data set and unpick it manually. So that's what I do. We get 25,000 train and test sequences. Here's what the first review looks like. Doesn't really look like English, right? So in fact, the way these data sets are often encoded is by having a mapping from word to an index. Typically, at least in this case, and I think pretty usually with the indices going from most frequent words first. So number one is probably the. And I have no idea what number 5,948 is, but we can find out. So it comes with this index that you can get that tells you what the mappings are. You make the reverse index from index to word, and then if you print out, here's the top 20 words. Burr, I think, is line break, but the others look like common words. Film is actually kind of funny, right? A movie would not appear very frequently, this frequently at least, in English in general, but in movie reviews it does. Yeah, and so one note, this means if we want to say, you know what, we're not going to look at really low frequency words because they're hard to make sense of, you can just cut off all indices that are above some index. Okay, so now we can actually make reviews that we can read. Right, and so well, this is our task, right? To read something like Bramall High as a cartoon comedy, running at the same time as some other programs about school life, such as Teachers, my 35 years in the teaching profession lead, and then I cut off after however many 30 words, but it keeps going. And the question is to read this whole thing and be able to say, is this a positive or negative review? For this first one, right, from the first 30 words, I can't tell you. It's not at all clear. Some of the others, like the third one, brilliant overacting by Leslie Ann Warren, etc., suggests that maybe that's going to be positive. So you never know. It could, at the very last minute, say, but despite all of that, it was terrible, etc. Here's another good one. Where was it? This is easily the most underrated film in the Brooks canon. That suggests it's a good review. And then, sure, it's flawed. That suggests it's a bad review, and so on. Okay, and then the labels are 0 and 1, positive and negative, half and half of each. For processing these kind of text things, it's useful to understand how long they are. So I made a histogram of review lengths. You can see that the vast majority are under 500, and some go up to about 1,000 words in length. And at least the way we're going to tackle this first, we're going to end up using fixed length windows, so pad short reviews and cut off long ones. So it looks like, for this data set, 200-300 would be reasonable length.
What's the first chart?
So I compute the lengths of all the reviews, how many words. And so this is a histogram, and this is just a cumulative distribution to see if I cut it off, say, at 300, that's going to give me 80% of them untouched, and shorten 20 of them, the length of the review in words. Yeah. So this is our problem, right? So given what we learned yesterday, it's not really clear how we might go try to build a classifier for this, I think. So let's come back to it. I guess one thing we could do, right? And in fact, I think I may even have an example of trying to do this, is just, pad short reviews to some fixed length and cut off long reviews. So say that we're going to pick 300 words, treat that as a 300 index vector with just those numbers that we have, and then try to train a neural network to say, look, given these, given these words, predict a single output, yes or no, positive or negative. Do you think that would work well if we did that?
I think it should work relatively well if most reviews are long as 500 words capturing or review.
Sure. Let's even just say let's just only focus on the short one. So ignore the truncation issue. If I just give you 300 words as a vector of a bunch of numbers from 1 to 20,000 or something, and then say, okay, try to train the model from just the list of words to a sentiment, right? And the model is going to work the same way it worked yesterday. We're going to have a bunch of weights for each of those numbers, and we're going to have some hidden units that say detect something from your input, and after some number of hidden layers, we're going to say, okay, predict the output. So how would that work?
Yes and no. If you have enough data, get some reasonable performance. So if you have one document talk about diaper, okay, and that diaper is a positive review.
Yep.
Okay? But you don't have any other document talk about that diaper.
Yep.
So the next document coming with diaper, I can guarantee you give you positive review because diaper is positive. But
Yep.
the diaper doesn't mean anything at all. Right?
Yep.
So that's a data bias problem. So that's
Right. So ultimately, I think that's right. If you imagine, a data set that has kind of all possible reviews in it, or a huge subset of them, then of course, yeah, it'll work well enough if your network is big enough. But otherwise, you have, each of your words can have a value, like one of 20,000 different words or more, actually, in English, and individually, none of the words even mean anything as far as sentiment goes, right? Because you have to look at patterns of words. And so, yeah, you're going to learn things like, oh, if the word Brooks, or Schwarzenegger appears in the review, it must be positive because there was one example in my data set where that was true. But then the next one comes along, it's more or less random whether it's going to be positive or not. And so to actually generalize, you have to learn some kind of abstract general things, and it's incredibly hard to do that from 25,000 sentences where they're all using language in all kinds of different ways. And so one of the things that's the problem is that we have so many different words, and we don't have a good way to capture relationships. Well, the network would have to learn all possible relationships about synonyms and antonyms and things that modify, words that modify other words and so on. Instead, we're going to try to do a trick that really made natural language processing much better when people started using it, I think pretty recently, just a few years ago, called embeddings. And so the idea is, like we said, there's many ways to say the same thing. And so rather than trying to learn each of them individually, we're going to try to represent words in some more concise way, such that if two words mean the same thing, they have a similar representation. And if two words, for example, don't mean the same thing but have the same relationship to two other words, they might have this geometric, the same kind of relationship in this encoding. So we'll see what I mean in just a second. Yeah, you want to encode similarity between words, differences between words, and semantic relationships between words, and have a concise representation. So what that's going to let us do is solve these kind of analogy problems. And if you, in some ways, if you can capture those kind of relationships, then you understand language in a certainly deeper way than if you just have a random number for every word, right? So man to king, woman to what? Queen, right? And like that's trivial for us, but how do we get the computer to figure that out? And the approach is going to be embeddings, which is basically going to say for each word, we're going to embed each word in a vector space of some reasonably high dimensionality, so say 100 dimensions. So for every word, we're going to have 100 different numbers, right? Vector of length 100. And the idea is going to be to try to make these vectors encode these relationships. In particular, saying that, look, if I see these words kind of used in similar ways in English, then they should have a similar vector. It should be close together in this 100-dimensional space. And if I see them, like I don't see them in similar contexts, then they should not be close together. And hopefully we'll actually get semantic encoding out of that. And basically that's the approach. You look at a bunch of text. So this is an unsupervised kind of task. You just give it a bunch of unlabeled text, and you try to read it and notice things. It's kind of like I mentioned the statistical approach, right? You're going to look at what kind of words appear next to each other and what kind of words don't, and then you're going to try to train, just using gradient descent or some other optimization mechanism, a set of vectors such that, well, I guess I have a slide on this, right? Try to minimize the distance between the vectors corresponding to two words if those words appear more often. I think I have even more details. Oh yeah, okay. So I'm trying to see if what else to say. Does this make sense? Right, we look at a bunch of words, we say, look, there was a frog in the swamp, so I'm going to count how often the word swamp and frog appear next to each other within, say 5 or 10 words in my giant corpus of, billions of words. And I'm going to count how often the words artificial and frog appear next to each other. And so that gives me a bunch of probabilities or counts. And then I'm going to say, I'm going to start with random vectors for each word, and I'm going to try to shift them around so that the distance between two vectors is small, where the count for the probability that two words appear next to each other is high. So roughly speaking, sort of to get a more concrete cartoon example of this, first you start with random vectors. Then you say, okay, I'm going to try to predict, right? Just build like a linear regression model, given the distance of two vectors, how far, say, the frog and the swamp vectors are right now. I'm going to try to use that as a predictor of, in real life, actually the log frequency of seeing those two words next to each other. And then I'm just going to update the weights to make that prediction more accurate.
What's the dimension of this word? Is that 10, 20, 100?
So the dimension it's just up to you, but people tend to use something like 1, 2, 300.
Okay. And so initially the number is randomly assigned.
Yeah, you pick a random 100-dimensional vector, and then you just do optimization and say, okay, compute your error in this prediction, and then say, how can I change all the weights for all the words to make that error slightly smaller? So you can basically just do the same thing we were doing yesterday with gradient descent, and say, what's the derivative of the error on my data set as a function of each of these parameters, take a small step in that direction, recompute, repeat. The nice thing about embeddings is that you can just go download one that's been pre-computed for sort of various English data sets. Of course, you can also train your own. But to do that well, you need a lot of data, and it takes time.
But for every vector that the categorical variable is the same. So, for example, you have 300 dimension.
Yeah.
So for frog and for swan, they have the same column length for all 300, or they are different.
Right. So the question is whether the sort of vector indices mean the same thing for different words. Yes. I mean, well, yes, that's the hope, right? When you start, they're just 300-dimensional vectors with random numbers in them. But what you hope is that by doing this process, it ends up, through this optimization, deciding to use the various different elements of your vector for different kinds of concepts, right?
So in this case, so the dimension of the vector is supposed to be your vocabulary size, because we were talking about.
No, so unlike yesterday, we were doing something like one-hot encoding, where we would say, okay, for this particular label, I'm just going to have a 1 in location 64 and a 0 everywhere else. Now we're not doing that. Now we're going to say we're going to map the word frog to some point in a 100-dimensional space. That's not at the extreme, so it'll have fractional values like I'm showing here, and we're going to map swamp to some other point, and we're going to hope that because those two words kind of are related to each other, they're going to be reasonably close together in a 100-dimensional space. So along at least some of the dimensions, they're going to be close together. For example, there's probably a dimension that says, these are sort of nature-related things, and they're going to be close together in that relationship. And they might be far apart if there's some other dimension that encodes like aliveness. And so alive things have a high value, and non-alive things have a low value. That's what you hope you will get out of this training. And it doesn't by any means mean that you're going to actually end up with individual indices corresponding to that, right? You could have some other direction in this 100-dimensional space that involves a bunch of the elements, but still kind of lays things out on some spectrum.
So does that mean all the index is the same, right? So we still try to make sure if you have 300 dimensions, all the index mean the same thing.
The indices into the vectors, don't mean anything semantically, but what they do mean, the idea is when you compute distance between these vectors, right, you're going to look at distance in each dimension separately. So in that sense, I'm going to compare, the first vector and the second vector along the first dimension, second dimension, and so on.
Because to me, if we do this way, all the indexes will be similar to a latent variable.
Yeah, in some ways.
So somewhat, right? So you have a latent variable. So the word frog actually was composed by 300 different combination of latent variables. So
so that's one way to think about it, right? You can think like, look, I'm going to encode this word I'm going to assume there's 300 different things that matter. Well, not just that, 300 things, combinations of which might matter. And so then for each word, I'm going to pick kind of some value for each of those 300 things. And then hopefully those things will combine in a way that encodes what this word means. Let me show an example. I think this doesn't animate in here. This is sort of a cartoon version that shows the idea, right? You're hoping to get values. This is in 2 dimensions, obviously, such that if you take relationship between 2 words and you move that same relationship in a geometric sense, you get, you can do these kind of analogies, for example. So a direction, in some ways, right, encodes gender. And so you hope that, okay, if I go from son to daughter, you go from uncle to aunt, etc., in this direction, in this space, wherever you are. And there's another direction that encodes, higher status, right? So you're going to go from duke to king, or something like that.
And does that kind of speak to the latent variable, or kind of like latent dimension? Because you're adding all these different dimensions and it's capturing things like gender, when it's not explicitly said in the text, like,
Right, exactly. You're capturing these hidden things, and the interesting thing is, right, this is an unsupervised learning problem. So it's not like anyone said, "Oh, I think gender is important, so let me try to encode it." All I said was, please make words that go together be next to each other in this crazy space. And when you look at it, for some particular set of words, it turns out to encode you're like, oh, that's interesting. This direction seems to be gender. This direction seems to be status. This direction seems to be something else. So here's another example from a visualization of one of these embeddings, right? Like a bunch of number words are all relatively close together, and small words, right, 2 through 9, are all closer together than 20 and 100, and so on, and doesn't. One interesting thing is note that 1 is not in this picture. Because, well, why? It's sort of a hard question. Remember that we fed this thing just a whole bunch of English text. So why might the word 1 be treated differently than the word, 7?
The 1 has many different meanings.
1 has different meanings, right? It's not just a number. It's also things like, oh, someone went over that way. And, one may think that 1 is a number, but 1 would be wrong. And so in the end, you're still encoding just 1 vector for this number. And so I'm sure it's not that far away. This was just a small snippet of a visualization projected in 2 dimensions from, I forget how many this was, 1 or 200. But yeah, because it has multiple meanings, it's going to end up being treated differently.
But then, would you be able to actually really encode like 1?
Right. So the question is, that's a problem if you're trying to deal with potentially a problem. If you're trying to read text about numbers and it uses 1, 2, 3, 4, 5, you may misinterpret things. And so there's still, there's a ton of work. And usually what people end up doing often is actually some combination of these statistical methods plus the, giant databases of words and their meanings, et cetera. Like they're not mutually exclusive. And so you might actually try to say there's a problem called word sense disambiguation that says, okay, for every word in the sentence, if I know it might have many different meanings, try to figure out which one it is based on the context. And so, for example, if you have a sentence like 1 + 1 = 2, you might be able to figure out like, oh, I'm talking about numbers. So 1 is probably, because there's a plus and there's a 2 in the sentence. So 1 here probably means the number sense. But yeah, language is hard. If that's one of your takeaways for today, that's probably good because we get some sense of how to do this, but really, obviously, just like all the other things, tons and tons to read, lots of classes you can take, and you can spend years learning about how to do natural language processing. But yeah, so here's another cluster, right? There's a bunch of words related to school and schooling and teaching that all seem to be relatively next to each other. Again, when projected down to 2 dimensions. So in general, there's still going to be more structure that isn't captured here. And like I mentioned, some people at Twitter and Google and Stanford and probably other places have done this on large data sets. And you can just go download an embedding and use it. You can also download an embedding and then tweak it based on your own data set. Just like we did sort of tweaking of a pre-trained model. You can think of this sort of as a model. It says, look, what's the best mapping for each of these words? I can adjust it using gradient descent based on the error metric I'm trying to optimize on my training data. So you can do that. And if you want, you can also train your own. If you have a big enough data set that it makes sense. Note, by the way, right? So Twitter, Google News, and Wikipedia, and the giant sort of newspaper corpus, they are going to have different properties, right? You sort of expect that if I'm trying to make an application for processing, financial analysis, Twitter is probably not the best embedding. Google News may be better. If you're trying to do, I don't know, general English text, the Wikipedia one might be better. But yeah, like we saw in the film reviews, there'll be things like word frequencies that are different in different data sets. Okay, so let's go back and actually look at how one might do this in sentiment analysis. And in particular, what we're going to do is, now we're going to apply embeddings. So rather than trying to have the network learn about each word completely independently. We're going to use an embedding for each word, pre-trained one. And then we're going to try some of the methods we already did before. Right? So we're going to pad things to fixed length. We're going to do just a regular, fully connected neural network. I don't remember if I actually said this yesterday. Often also called the multi-layer perceptron. A perceptron is basically just that one layer, like linear regression model. And the multi-layer perceptron is just a bunch of them. So that's kind of your standard multi-layer neural network. And then we're also going to try a one-dimensional convolutional network, where we're going to say, you know what? Let's not look at all the words altogether. That's too hard. Let's look at small windows of the sentence, right? So 5 or 7 words at a time, and then have multiple layers that combine to more complex ideas after that. So I'm going to stop this and go to the Batmobile. No, to the code. Hide this stuff. Right, so this is going to be our plan. Right, load the data set again. Get rid of. Can you read that, by the way? Should I make it bigger? Get rid of really rare words, because it's going to be hard to learn anything about words that only appear a few times. Pad to fixed length. Replace each word with an embedding, and then build our networks. So, yeah, Keras is great and has a bunch of useful things for text processing as well, right? So you can go get things that will, tokenize. There's a function to do this padding for us. We have a bunch of things we already know. I guess all of these we know. Now we're going to have one-dimensional convolution and max pooling.
Just a quick question. I tried running this in DSX, and I got an error on the categorical. Do you know if that's an error 2.0 or is it just?
Yeah, let's look during the break. I should just pull up the documentation for both versions. It might be a 2.0 thing. I think there were a couple of breaking changes that were sort of trivial, like they renamed a couple of things and moved things from one package to another. And I tried to keep it consistent, but I only realized that DSX had a different version after I'd already made some changes. So but we can fix that easily during the break. Right, so 1D convolutions, embeddings. You can ignore this LSTM thing for now. We're not going to use it just yet. Right. I have tokenizer twice, whatever. Okay, this is all familiar. We load the data just like we did the other day. Right, so GloVe is one of these word embeddings from Stanford based on Wikipedia. I picked the 100-dimensional version. There's versions with 200 or 300 as well. This one's just smaller. I said, okay, let's use only 20,000 words. Keep only the first, actually, I think the last 300 words, if it's longer than that. So we pull out the embedding. It has 400,000 different words in the embedding. So English is kind of verbose. Not verbose, wordy, maybe, is a good word. We're not going to use all of them, right? We're going to only use 20,000. So we need to do some shuffling because of that bug in Keras. So pad sequences. There's just a function called pad sequences. You tell it, okay, here's my 25,000 examples. Please make each of them fixed length. And so that's what it does. Now we have 25,000 by 300. Right? These are still just one number for each word. So we haven't done the embedding yet. So here we're going to say, okay, every number that's bigger than 20,000, we're going to replace with 20,000. Well, 19,999. So now we've gotten rid of all the really rare words. And instead our network is basically going to say, this film is rare word, something, right? So we're just using a fixed number for all the rare words. Hopefully it'll generalize better that way, right? Maybe it doesn't know what a rare word means, but at least it's not going to be able to memorize, oh, I saw this word once. It means it must be really positive. And now we're going to replace. you're trying to, so in theory, you shouldn't do any of that. But the idea is, if there's some word still, right? If embeddings will definitely help, right? Embedding means that it'll be a little bit harder for the network to memorize. Oh, whenever I see 50,744, I only saw that once, and it meant it was positive, so I can just learn a really strong association from that word to positive. With the embedding, you won't be able to do that quite as easily, because it's going to have to learn, a mapping that sort of, well, potentially a mapping that can generalize to other words, especially for the convolutional network where you have the assumption about invariance. But still, if there's a vector that you only saw at once, it might learn something kind of too specific to that vector. In general, even more so, I would say, than the image processing stuff we were doing yesterday, it's obvious that none of the things you're doing are quite right. And so you really just have to try different variations and see, like, does this seem to do better or not, given the limited amount of data that I have, which is always limited, right? And so, yes, if I had all possible reviews ever and I could train my network on them, I wouldn't need to do any of this if you saw everything sort of often enough and had enough data to generalize. Because we don't, in this case, we really don't have much data, right? We have 25,000 sentences, and data set has more than 25,000 words. Not to mention all the words it doesn't have that could appear in the next review. So have to do something to help kind of make the problem a little bit simpler to deal with our limited data. Right. Does that make sense? Kind of.
I'm not sure if that. I would probably try without.
Yeah, I think that's totally reasonable, right? Try without and see what happens. And then if you can figure out, the trick is then figuring out why it's making certain mistakes. But I guess the one general takeaway is this is a common thing people do to make language problems easier, right? They say, look, I don't want you being too specific based on things that appear only occasionally. I want you to learn things like, oh, if I said this film made me really angry, like that means it's terrible no matter, what other random things you say next to it.
Because you have a lot of mistyping,
misspelling. Typos,
so
yeah.
There are a few that proper words, so you don't really want that. So if you want to pick up the word has it's higher count, so it's more meaningful. So it's more representative. And typically, 20,000 words is already a lot of words. Right?
Yeah.
So when you go to 400,000, a lot of from 20,000 to 400,000, probably long tail, they have a very, very minimum count. So you typically don't want to have your system biased by this long tail. The vocabulary.
Yeah, so there's things like, a lot of those 1,000 words are typos, for example, which, maybe means you should run a spell check and spell correct before you even start. But somehow, making your problem simpler is useful. Okay, so let's come back to the code. And again, I'm not going to go through every line, but basically now we're going to make this embedding matrix, right? For every word, we're going to have a 100-dimensional vector. We just go look at our embedding and look up for each word that we still have what the vector should be. Sometimes it's not there, so we just leave it at 0. And then Keras has this embedding layer that you can just put in and say, look, here's my words, here's my embedding matrix of the weights that the network should use to look up the word and get the vector. And right now we're telling it, don't train this. If you don't put that in, or if you make it true, then as you train your network, it'll actually try to adjust the weights in the embedding matrix as well as the weights in the rest of the network. So now let's make a model.
What happens if the embedding
We just leave, so we start with a matrix of all zeros. And so if we don't have it, we just leave it at all zeros. Otherwise, we replace it with the vector that's in there. Yeah. Right, so to actually make our network, once we have the embedding, turns out to be very, very similar to what we did yesterday. We just say, okay, we take our input, and then we apply the embedding layer. This, by the way, is using the Keras functional API, where you actually sort of basically pass the previous layer into the next layer, and that tells it to connect them in the same way as sort of implicitly it was doing in our sequential model we were using yesterday. Again, you can look up the docs for the details. It's pretty straightforward. Right, we basically say, look, here's the previous layer, feed it to the next layer, repeat. So we have our embedding. We flatten it into one giant vector. So instead of whatever 100 dimensions by 300 words, we're just gonna have a single vector of 30,000 numbers for each sentence. And then we just have two dense layers who drop out, and we're gonna predict positive or negative. Same optimization, still looking at accuracy. Right now it's binary cross entropy because it's binary classification. Yeah, dense network with 30,000 number inputs now. That's a whole lot of parameters, right? So it's like 7.7 million parameters that we're training, plus 2 more million parameters that we're not letting it mess with. That's the embedding. So hopefully from our 25,000 sentences, we're going to get reasonable values for 7.5 million parameters. What are we trying to fit? So this is our data set, right? We have our inputs are sequences of, here's 300 words, which we're going to replace with 30,000 numbers for the embeddings. And the output's going to be 0 if it's negative and 1 if it's positive. Or possibly vice versa, I don't remember. So we just run our model.
Sorry, you said the embeddings, those weights, that's not going to be changed.
Right, so up here we said, don't train it. You could train it, but the problem is, again, you can, without enough data, it's going to be able to make it too specific for your training data, and it won't generalize. So here I decided not to mess with it. Besides, there's already enough parameters to learn in the rest of the network, at least with this fully connected approach, which is a preview, is not really a good way to go. Right, so I did 25 epochs, accuracy, still going up and flattening out a little bit. Quite good, really, right? We're getting 95.4% accuracy in the last epoch. Are we happy about this? You're shaking your head no, why?
Accuracy is 70%.
Right, because the accuracy we actually care about, right? This is overfitting is still a problem even though it's Wednesday.
This is the same.
So really, it's not right. It's a binary task, and it's both kind of bad and surprisingly not random, which is interesting, right? Even with this kind of stupid architecture, which is trying to connect all words in the whole sequence to all other words and learn all these weights, it's able to pick up some kind of pattern that seems to generalize, right? So
We also don't know how many positives and negatives.
no, so that's a good question. I guess I didn't skimmed over that too quickly. The data set is balanced, so it's exactly half and half, positive and negative examples. Yeah, because obviously, if it was like 70% one or the other, then you could just have a really trivial predictor that says it's always positive and it'll be right 70% of the time. No, but here's exactly balanced. So somehow it picked up something pretty quickly, actually, just after a few epochs. But then it's not really running anything after that. You're just overfitting. In fact, if you look at the loss, it's actually getting worse. Yeah, and so look at the test score, not so good. So convolutional network is, again, one of those things that's, again, is obviously wrong, but may still be a better thing to do. In fact, almost certainly is a better thing to do, given limited training data. Let's say, you know what, I'm not going to try to learn all the relationships about all the words separately for each position in this 300-word sequence. I'm going to make the same kind of assumptions we made yesterday to say, look, if this film is terrible, means it's negative at the start of the sequence, it probably means the same thing in the middle and at the end. And so hopefully, if we look at adjacent words and then build up higher level structure after that, that will help us have a much smaller number of parameters, hopefully be able to force the network to not overfit quite as much. By the way, I guess I probably should have mentioned, and maybe I should have done an experiment. Dropout in that first network was almost certainly the thing that made it do anything at all. Right? So if we go back here, I have 50% dropout in the middle of my network between the dense layers. And so what that means is at least it can't just like memorize each of my 25,000 inputs using some of these weights just for each one test sequence, and say, oh, as long as I see the word whatever, word 494 in this location, then it's positive, right? Because the network has more than enough parameters to just encode directly, like memorize the input, but the dropout makes that much harder for it to do.
If the dropout wasn't there, then when we're looking at performance of the validation set and the training set, we see even a wider gap there.
That would be my expectation, yeah. So we could, actually, it could be kind of fun to rerun this later without the dropout. I would expect actually training to be even faster and go to 100% pretty quickly, and validation to actually be closer to 50%. So dropout is pretty magical, right? Still, like with 25,000 examples, we were able to get some kind of reasonable values for like 7.5 million parameters, which is crazy. I mean, to be fair, each of those sentences has 300 words, but still crazy. But now let's do 1D convolutions. So let's see, what is this doing, right? So we say we're going to take a convolution. We're going to have 128 features, like we had feature maps yesterday. Now it's just 1D. And we're going to have windows of size 5. So before we had 3 by 3 or 5 by 5. Now it's just a one-dimensional filter that we're sliding along. Activation is still ReLU. And we're going to do max pooling more aggressively than for images. So we're going to look at sort of groups of 5 words at a time, and then take the maximum value for each of these features for every 5 words. So it reduces dimensionality quickly. Again, because we don't have much data, I want to try to have a relatively smaller network. So we do this a number of times. And yeah, let me flatten the vector to get rid of the, basically be able to feed it into a dense layer. Let me have one more dense layer, just 128 units, and our classification. Same training.
We didn't put any dropout.
I did not put any dropout here. I forget if I have an example that has dropout afterwards. You probably do want dropout still. Yeah. So do you need dropout? The convolution structure itself is a regularizer, right? It's making you say, look, learn a set of weights that's sort of general across the whole image, not just at one location. Definitely still dropout can be helpful. In particular, often people will do is put dropout in the dense layers at the end, right? So you can, yeah, here, or if you have multiple dense layers in between them. It's not, again, it's a rule of thumb. In general, really the rule of thumb is, right, we're going to look at the learning curve. If our 2 lines diverge really quickly, that means we need more effort to make it generalize, right? So do worse on the training data, but please do better on the validation data, because that's what I care about. So yes. But to start, let's just see what just convolutions do. So now, right, we still have our 2 million parameters that we're not going to mess with, but now we're down to some reasonable number of trainable parameters, right? So 250,000 instead of 8 million. And we train it. It's convolutions again, so it's actually somewhat slower to train. And now it's better, right? The lines don't diverge as quickly. And I also trained it for fewer epochs because it was pretty clear from the last time that, after a little while, it doesn't really help anymore. And it's better. It's still, it's noisy, right? So it's not really clear exactly what the number should be, but it looks like we're around 80% generalization instead of 70. So that's better. And I think there was some bug with this OSTM thing, so I'm going to skip that for now. Yeah, so again, I didn't really try to tune this for performance too much. You could obviously change a bunch of the parameters and see how well that does. You could also try to add more regularization, so add dropout or add weight penalties, and see if that can get you a little bit more of a boost. But so far, still, as you may have noticed, no recurrent or anything, no new kinds of networks, but just embeddings and then some tricks to kind of wrangle your, the complexity of language. Okay. Any questions before we move on to new kind of network? Are we getting anything from Slackstream? Okay. If you're watching online, feel free to chime in with questions or comments. All right, so recurrent networks, right? Time and sequencing can matter in networks. And so we mentioned this actually earlier, right, Greg? You said this at the very beginning, like, hey, sometimes we have things that refer to things that we said in the past. And wouldn't it be nice if we had a network structure that could read a sequence of potentially different length and somehow encode things that were important to remember from what it saw before, and use that as information in addition to what it's looking at right now to do something. So yeah, that's what recurrent networks are going to try to do for us by having some way to represent the past. And the idea is, you can kind of get the intuition from these kind of high-level diagrams of how the information flows, right? So far, all of our networks have had these straightforward, feed-forward structure where we take our input, we feed it to one layer, to the next layer, to the next layer, to the next layer. At some point, it goes to the output. And there's no cycles or anything. So what we're going to do is really just add one more little line. This thing called a recurrent connection. And we're going to say, you know what? If you have some state, right, some values, some activations in your hidden layer, we're going to let you use those as input to the hidden layer, or if you have many layers, to the hidden layers as you go. And this becomes maybe easier to understand, or at least a different way to look at it. I think it's useful to look at both. Is the what's called an unrolled view, where we're going to say, look, we're going to feed this network a sequence of information, let's say words, one at a time now. It's not the whole sequence of 300 at once. We're going to give you just one word at a time. And for the first word, it's just like it was before, right? We have our input. We're going to have some hidden layers and some output. But then when we feed in the second word, we're going to feed in the input, right? So the word embedding for the second word. But we're also going to say, you know what? We can actually look at what the hidden layers were after the first word, and also have weights for how to transform, how to add those in to the values that we're going to use for, to our hidden layer. So basically, your input now becomes the state from before and the new word. And you can combine those. It's still going to be the same, weighted sums and activation functions, and then produce an output. And then when you feed in the third word, now you again feed in the hidden state from the second word, et cetera. And so, this gives the network some capacity to say, you know what? If these particular values in the hidden state are positive or high or low, that means something that is important to remember about the past. And again, the hope and the power of these networks is that it'll figure it out, hopefully, what kind of things are important, right? So it might decide, you know what, I'm going to use these cells in my hidden layer to encode something about the past, and I'm going to use these other ones to really focus on what's going on with the current input, and I'm going to figure out how those things should be combined in, for future words, just by doing gradient descent and saying, like, look, if there's a good set of weights that can behave well on this problem, hopefully it'll find it. Yeah, right. So again, if you look at it in this way, it just has the cycle that says, look, over time, we're going to keep feeding this back. You can think of it in this unrolled way, where you just see each copy of the network over time. One thing is that there's variance in this. So for example, for our sentiment analysis thing, I don't really care about the output until the very end, probably. Right? I'm just trying to predict one number. If I was trying to, for example, translate each word as I went along, or say each word as I went along, you would actually want the output at every point. And yeah, so what does this mean for our actual network structure? We're just going to have one more set of weights that says, how do I, what do I do with the vector that is the previous hidden state as I feed it into my new hidden state? And so more parameters. Yeah, and in terms of how to actually combine this, I don't remember if I actually put the math, but really it's just addition, right? So we're going to take our weight vector, our old w times x weight vector, and we're going to add a new vector called, say, u times h, which is the previous hidden state activations. And then we're going to apply an activation function, et cetera. So no magic there, just addition. Magic is always in the weights. I think I screwed this up in terms of animations. Yeah, OK. So, well, in convolutional networks, we got a significant amount of power by making certain assumptions that helped us reduce the complexity of our model. And we're basically implicitly doing the same thing here. So where are we making assumptions about certain kinds of invariance in this model? Or maybe in this model. Are there parameters that could be different that aren't, that we're insisting are the same? Or are there certain kinds of locality that we're insisting on? Or we could have more arrows than we actually do? Go ahead.
I don't know.
Whatever you learn from the past, you can carry over. But I'm not quite sure about only one layer, only one output. Because if this is your input data, if you learn from the past of 50%, you already know what's going on. So you recover.
Yeah, so I think you're getting at something here. We're letting the network remember the past, right, and depend on what happened in the past, but we're doing it in a very limited way, right? Where imagine you have a sentence or some sequence and you've read through the first 10 entries in it. In general, there's nothing saying that I can't make the next one depend on all 10 previous inputs, right? So if I have x1, x2, x3, x4, x5 could depend on all of them. And instead, we're making an assumption that says, look, we're going to force the network to remember everything that might matter in its hidden state, and we're only going to have sort of this one-step connection from t to t plus 1, not from t to t plus 1 and t plus 2 and t plus 3. So you could imagine way more arrows sort of from hidden states from further back in the past. People sometimes actually try that because if this is for short sequences, this is okay, but for really long sequences, this is going to be difficult for it to remember. Keep dealing with the new input as it goes, and still remember, oh, 3 paragraphs ago we introduced a new character, who was named Diana, and when you refer to Diana, like that's who we're talking about, because you only have so much capacity So that's one connection, right? Sort of locality in time. We're saying you have to remember everything, and if it's relevant, you have to keep it long. And the other connection is invariance assumption, where I sort of implicitly said, and you can kind of see it better maybe in this view, that there's weights that we're trying to learn in each of these connections, and we're only learning kind of 3 sets of weights, right? We're learning input to hidden, hidden to hidden, and hidden to output weights. We're not learning a different set of weights for the first element in our sequence, and then a different set of weights for the second one, and a different set of weights for the third one, which in principle you could. And in fact, if you really think about sort of the true model of the English language, almost certainly you'd want to, right? You might want to treat the first word of a sentence somehow differently than what typically a second word or a third word. But we're going to say, you know what, that's too complicated. We're going to insist that you use the same model at every time step. So this is where I screwed up the order of my animations. But right, same parameters at every step. And yeah, only one directional, one-step arrows. Training. Backpropagation. You can still compute the derivative of, how do I need to change all the weights or each weight to, reduce the error on my training set. The calculus still goes through. You do have to remember kind of what happened at every time step as you went along, and then add up the contributions to the weights from each time step. In practice, it's hard for long sequences because essentially you can think of this as just one really, really deep neural network, right? If you have a sequence of 100 inputs, your input number 1 goes through like 100 different layers before it gets to the output. And so if you try to backpropagate your error, it's sometimes called backpropagation through time, but really it's just backpropagation through a network. By the time your gradient of your error gets down to somewhere near the beginning, it's either gone to 0, or sometimes it goes the other way and it actually gets really, really big. So there's kind of these 2 symmetric problems called the vanishing gradient and exploding gradient problems, which can happen in regular, convolutional or MLP networks just as well if they're deep. But sort of by definition, the recurrent networks become deep as you try to deal with longer sequences. And so, I don't want to spend the time it would take to get into all the details of how to try to fix that. Roughly speaking, you have to be much more careful in how you train these networks. So there's some initialization tricks that you can do to try to make sure that your derivatives aren't going to get too big or too small. It helps to just try to find a way to, solve your problem by only looking at short sequences. And there's some other tricks. So one is called LSTM, which basically adds a little bit more parameters to your network to have it learn, rather than just overwriting your hidden state at every time step. It basically has what's called gates that say, you know what, let me just decide whether or not I should overwrite this particular cell, or whether this would be a good time to just leave it alone. And so the trick is to make that, I think I have a picture. I do have a picture. I don't know how useful the picture is without reading much more. But basically, you make these continuous things that you can still do backpropagation through because they're differentiable. And you say, yeah, I'm going to learn a separate set of weights to decide when to overwrite my hidden state and when to not overwrite it. And similarly, when to have this hidden unit contribute to the value that I'm outputting, when not to. And that can help the network. Again, this is intuition, right? In the end, it's still just linear algebra with some nonlinearities, but it seems to help the network learn what stuff to remember. And so, for example, if you had a sequence, as a toy example, if you had a sequence that had real data and then just sort of dummy placeholders that didn't mean anything, every other element, it might learn, oh, when I see this placeholder, I should just not touch anything and just move on. Whereas without this, it would have a much harder time doing that. Sorry, I'm trying to play time management games here. Well, maybe I'll quickly look at this. Two points, I guess, on LSTMs further. One is, if you're using Keras, you can just say, I want an LSTM layer with this many units, and it does all the magic for you. Two, if you are actually planning to do that and do tech stuff, there's definitely more that you can and should read to learn more about it as you start to experiment. Where is my text generation thing? I think I didn't open it. Right, so here's an example that I modified slightly from a Keras example. What it's going to do is try to make a model of language. So we're going to feed it a bunch of text, in this case, all of Nietzsche's writings. And it's going to try to predict, using the history of the, character by character, using the characters we've seen before. I think in this case, we're going to feed it like the last 40 characters. Try to predict what the next character should be. And if you can do this really well, then somehow you're capturing how language works at the character level, right? And you can say, okay, given that this is what I just saw, well, I should just spell things correctly, but I should have a space, and the next word is most likely to be such and such. So this model isn't actually that useful for application, but, well, it's useful for making funny Nietzsche-looking text. But if it works well, it's capturing something about language that you can then use for actual applications, like, I'm trying to make a chatbot, and I want it to spit out things that look like valid sentences, right? If you had a corpus of a whole bunch of, back and forth discussion, you might try to say, okay, let me try to make this thing predict what you should say, given what the question was. And if it can do that well, then you'll be happy. In general, for that application, you want to combine like a language model that says, please spit out valid English, with a more content-based model that says, please also answer the question correctly. And you don't necessarily want to train those at the same time. But that's more complicated. I don't have an example for that. But here, right, we just read a bunch of Nietzsche. We are going to do the same kind of thing where we're going to replace characters with a number, and then we're actually going to have an embedding. Is that right? I don't remember what I did here. So yeah, here's all my characters in the text, including some weird ones that don't happen very often, but didn't get rid of them. We're going to do a sliding window thing to get training data. So again, we're trying to predict what the next character should be. So the way we're going to make training data, we're going to take sequences of length 40 as the input, and the next character as the output. So those are going to be X, Y pairs. We're just going to slide, take steps of 3 characters at a time. So in the end, you get 200,000 or so sequences that look like this, right? Supposing that truth is a woman, that the next character should be H. Is there not space? The next character should be G, etc. Right? This is our training data. Number. Yeah. Anyway. So step 3, I think, is just a way to reduce the size of the data and make the thing train faster. Yeah, in general, there's no good reason to do that. I don't think. I mean, in principle, yeah, more data is better, right? In some ways, it's a little, you're making the network learn. No, I think it's really just to reduce the size. What's happening here? Right. Oh, right. So there's no embedding. We're just doing a one-hot encoding for the characters. So we're going to replace each character with a vector of length, whatever it was, 59. So we're going to have these giant, well, not that giant, but 40 by 59 matrices for each of these. Each sequence is going to have a vector of, a one-hot encoded vector for each letter. So we do that. Here's the first letter of the first sentence, right? A whole bunch of zeros and the 1 here somewhere. I made some pictures that weren't very informative, but kind of interesting, of the one-hot encoded vectors. Yeah, that's just all the characters are used, including some weird ones, right? Punctuation, numbers, all the alphabet.
So there's no notation.
Yeah, so this is all lowercase. Which, you could make a model that doesn't have that. It'd be more complicated, but eventually it would definitely learn when to capitalize things. I think I have a link later. There's a great Karpathy again blog post from a few years ago. I think it's called The Unreasonable Effectiveness of RNNs, of Recurrent Neural Networks, that he basically did this, but trained it on a bunch of different things like LaTeX and code, and actually got kind of reasonable and hilarious looking things in addition to text.
Are you running the word-based or you're running character-based?
This is character-based here. So trying to learn one character at a time.
Yeah,
Model.
It looks like a character-based.
Yeah. So again, in terms of the actual Keras model building, it's pretty similar. Now we're going to use LSTM as the sort of recurrent units that have this memory and these gates to decide what to input and output. Then a dense layer after that, softmax activation after that, as usual. Well, dense layer to the number of characters, right? And yeah, so pretty simple kind of one LSTM layer model. They're hard to train and they're slow to train. So I didn't want to make it more complicated to start. Okay, I'm going to skip this, but you can read through it if you want. I'm also going to skip this. This is basically just, so this is sort of useful. When you make this kind of model, you have to decide, you're going to get a probability distribution over the characters for what the next character should be. And you have to have some way to decide which character to actually pick when you're generating your text, right? Because the prediction is like, A probability 0.6 and B probability 0.2 and C probability 0.01 and so on. So there's this temperature parameter that we use to basically decide how much to explore and how much to always take a thing with the highest probability. If you take the thing always with the highest probability, it's going to be more likely to just output the same thing it learned from. If you have, if you tell it to explore more, it's going to be more random. It's going to make more mistakes, like typos, etc. Like I told you not to put a B, but you did put a B anyway, kind of thing. So basically, if the temperature is low, it means like always take the thing with the highest probability. And if the temperature is high, then it's more even distribution across things.
It's just random.
Yeah. So we have the sample function that says, given a set of predictions, right? So here's what probabilities are for the 59 different characters that it could be. Pick one. And then once you pick that, then you can feed it into the network again to pick the next one. So it's using just like a normalized exponential thing. Okay, so this is just the code to actually run the thing, train it, and print stuff out. But the fun part is the actual output. So let's look at that. All right, so here's it starting. And you're saying, please, be pretty conservative. Always take the highest one. And you get stuff that actually already looks vaguely like English, right? It's not just like a random sequence of characters after one pass through the data. But it just gets into loops. And it's like, great, the self, the self, the self, the self, the self. Maybe that's Nietzsche. Right, so if you say, actually try to be more random, then it doesn't get into loops as much, but it also makes up words more, right? Langually, in the Sues. And so, again, it's kind of amazing that after one pass, it's already got captured a lot about language, right? There's spaces. It looks, if you step far enough away, it looks kind of like language. But it's still not very good. If you run it for a while, and again, I decided rather than dealing with GPUs, etc., I would just run it overnight. So it took a few hours, maybe 4 or 5 hours on my laptop. You actually get stuff that starts to look like language, right? And so here with high diversity, it's making all these typos. With lower diversity, it's not making as many typos. There's still some. Presentado. But it's getting into loops again more. But yeah, so somehow, it's not very good. It hasn't really figured out how English works. But at the same time, given that it's looking at one character at a time, it's remarkably good. It even, for example, this could be a complete accident, but it could be not an accident. Closing quotes. Right? So it remembers, like, oh, when I saw a quote, probably I should close it at some point. And it seems to mostly remember to do that, right? There's one quote, there's another quote. Clearly, good to so was a phrase that appeared somewhere in the input because it's repeating it a number of times, etc. All right, so I guess main takeaways there. These models are remarkably effective and can capture a lot without sort of really any understanding of the problem they're solving. At the same time, they're not magic, and they're pretty hard to tune and train. So if you end up using them, you will definitely want to read up more details. I'm going to skip the sentiment example.
So can we just summarize the previous example? So that what you want to do is you want to automatically generate text, the text generation. But based on what do you specify how many sentences you want to generate, or based on any initial starting sequence?
Sure. Yeah. Sorry. I guess I skimmed over a few things. So the question is, well, first, I guess, yeah, we build a model, and then you need to give it some seed text. So yes, right, because to start, you have to give it something that's okay, now how do I continue this? So we just picked a random part of Nietzsche to start from. And sorry, what was the second question?
So
and length, yeah. So then you also tell it how long in general. So there's multiple ways to handle this. In this case, I think it just says like generate, I forget how many characters, some fixed length. You can make models that actually know when to stop in two ways. One is to predict how long the output should be. So basically, first you run a model that says, I think I should give you 7 words back or something, and then just run your LSTM for 7 words. Or the other way to do it is to have a stop symbol as part of your alphabet, whether it's at word or character level, and to have your model keep going until it spits out the stop symbol.
So you give us the initial seed sentence, for example, 10 word, 20 word, and you want them to generate 40 words.
Yeah, in this case, it's characters. So you give it some characters, and you give it makes more characters.
More initial character, and then generate less following character. You are first. So for example, what's the normal setup?
Well, so again, I think in this case, it's I think it feeds it something like 40 characters and then generates a whole bunch. Really, I think it depends on your application. Yeah, you can give it just one character. It probably wouldn't do as good job early on, right? It might eventually sort of stumble onto English again. But if I just give you, B, like what's the next character? I don't know. It'd be interesting to try. Actually, I wonder what would happen.
The follow-up question is, why not use more base? So you don't have the
Yeah. So I think there's, why not use word-based, right? I think 2 answers, maybe, or 3 answers, I don't know. One is just for a toy example, character-based is just simpler, right? You don't have to deal with embeddings, etc. And you also need less text, I think, in some ways, because if there's so many more words that you would have to figure out how to do that. I think 2 is that if you can actually capture things at the character level, it gives you more insight into just the power of LSTMs. Again, just as an example. And 3, I think, with words, you have to actually have all the various conjugations, etc., and know which one to use. Which I guess it would figure out if you gave it enough data.
Yeah, that you can do post-processing.
you can do a grammar check and clean it up. Yeah, so I think, again, this is certainly not the way I would build like a chatbot, probably. I would not use character models from Nietzsche. But the idea is just to kind of get some intuition for the kind of, the kind of dependencies and the kind of structure that your network can learn, these kind of networks can learn.
Those OSTMs, they always initialize to 0. So I wonder whether people
Yeah, I don't know about if people have clever ways to initialize LSTM cells or any other cells, I guess.
I was thinking more like, for example, you could track of each cell like over like whole training set, the entire training data set. Like what is like
You could figure out some prior, perhaps. Yeah, I think, I'm not sure, right? In the end, you can make up for some of that with just weights. So if when you're training, you start at 0, it's going to learn weights that make it work well when you start at 0. If you have some other way to train it, it might work better. I don't know if that's equivalent to just sort of adding a little bit more capacity to your model to learn parameters. Yeah, I think you'd have to find someone who has actually done a lot more LSTM training in real life than I have to comment on that. Okay, let's talk about one more variation on the structure, and then we'll take a break. So, encoder-decoder. So far, right, we've said, look, I can give you an output for every input, or I can give you one output at the end, but sometimes I don't want that. Sometimes I want different types of things, right? So I want to translate a short sentence to a long sentence in a different language. I want to take an image and give you a caption, a description for it, or vice versa. And so, yeah, you can sort of have sequence to sequence, so the sequences are different lengths. You can have vector to sequence, where you have a fixed input, a variable length sequence, and the reverse. And the way we're going to do this is by kind of stapling together two networks. One called the encoder, which says, okay, take my input and just translate it into some representation that's a fixed size, that's useful for the next part of the network. So then we're going to have a decoder that takes that representation as input and just does the output. And so Jeff Hinton in the talk I saw called this encoding the thought vector, which I think is kind of an interesting way of thinking about it, right? If I ask you to give me a caption, describe a picture, right? You look at the picture, you have some internal representation of that picture in your brain, and then you describe it. And then I drop my water bottle. That's fine. Yeah, so for sequences, it looks kind of like this, right? You take your LSTM, you say, look, just encode me this sentence from English into thought vector. And then you say, okay, now decode this thought vector into German or whatever else. And this is actually what Google, for example, uses for their Google Translate neural network-based thing. And the cool thing is now, right, for translation, they can actually use the same encoding for all languages. So their current version, they had a cool blog post about this last year, actually does sort of all pair language translation in a single model, right? So they have a whole bunch of different encoders, and then they have a whole bunch of different decoders for different languages. And if you say, hey, I want to go from English to French, it uses the English encoder and then the French decoder. And if you say I want to go from English to Chinese, it uses the English encoder and the Chinese decoder. So that's kind of cool. In general, right, you can still train this whole thing end to end because it's really just one network. And you can also, I think I have pictures of this. Yeah, right. You can replace it if you have a single fixed input, say an image. You can just have a regular network that takes one input, has a bunch of hidden layers, produces the output, and then have the text, or the sequence on the output. So for example, for image captioning, well, I didn't actually get this example to work. So I don't know if it's worth pulling up the code. Oops, no, maybe it is. But I think it's, yeah, I'll quickly just scan through it. Yeah, so this is an, you know, how would you do image capturing in Keras? This is, again, just a sketch. It is not fully working code. But basically, we're going to encode images into fixed size vectors using, you know, the same model we had yesterday, which we know how to do, right? So we take your VGG 16 model that we loaded. We can preload the weights. And then we have a recurrent network. GRU is a variant of LSTM with slightly different set of gates, by the way. That's going to take that 128-dimensional representation and spit out a language model, or, you know, a description. And yeah, basically, you know, you can tell Keras to combine two models, right? So have an image and the language. Well, training data is for capturing tasks, right? A bunch of images and a bunch of sentences, right? And so what we're going to do is we're going to take the take an image and convert it into a representation that we think is useful. We're going to take the caption and convert that into a representation we think is useful, and we're going to try to make those representations be the same. And then we're going to say, okay, given a partial caption, predict the next word. That's going to be the sort of LSTM, well, let's use some GRUs here, part of the model. And fit the model on, you know, given the images and the partial captions, predict me the next word, and so on. I realize this is a little bit vague because, like I said, I didn't actually end up getting this working. But hopefully it's given you some sense of how you might do this. I guess before I go back to the slides, does this make sense? Kind of, maybe no? All right, well, fine. What do you think, Sri? Should we go through these application sketches?
How about we take a break?
Let's take a break.
Yeah.
We can talk about it after. I think it's more interesting when more people.
The applications are interesting. I think it's 10:15, it's probably the time for break.
All right, we're taking a break, and we will come back and talk about these applications and then autoencoders next.
We want to spend some time to go over